This video will go over section 5.8, which is on mass calculations in chemical equations. But before we start on this and do a lot of examples, I want to show you where to find the information in the reference packet when you are doing things from chapter 5. So this is part of the reference packet, page 2 of the reference packet that has this as the first page. So you go to the second page, and the bottom of the second page, from the Avogadro number to the percentage yield, are all about chapter 5. And so these are information that you can have on hand when you are doing your exercises. And so the Avogadro number and the definition of the mole is given here on top. The conversion roadmaps for to convert between particles and moles, or particles and moles and grams of one substance. You know, given one substance, you can convert particles to moles and moles to grams of that substance, or vice versa, grams of that substance to moles to particles, or just you know, between particles and moles, or between moles and grams. So this roadmap is in case you are dealing with just one substance. The bottom roadmap here is when you are converting between moles and grams of two substances in a chemical reaction. So for this, you will need a balanced equation, for example, with coefficient W, formula A, plus coefficient X, formula D, gives coefficient Y, formula B, plus coefficient Z, formula C. So let's say you have a balanced equation of that type, and for example, you have grams of A, you want to find the amount of grams of B, you know, following this balanced equation, and this is the roadmap that would show you the way to do this. You would follow that roadmap. And of course, sometimes calculations, you know, use only two conversion factors, and for example, start at grams of A and stop at moles of B, or they could start at moles of A and end at grams of B, right? All kinds of combinations are possible. And so this formula here is showing you how an example of what the calculation looks like when it's you know, properly set up. In case you are using the mass of a reactant to find the mass of a product. Okay, and that at the bottom is the percentage yield formula. So this video goes over section 5.8, which is on mass calculations in chemical equations. And this is called stoichiometry. It's a term you will only hear in chemistry. And if you are searching for help on this, you know, you can type stoichiometry and you will have that kind of calculations. So given a chemical equation, you know, with coefficient A, capital A is the formula, the lowercase are the coefficients, and the capital letters are the formulas of reactant and product. So let's, given that generic balanced equation, to convert the of one substance, let's say A, to the mass of a second substance, let's say B, in that reaction, we will need the molar mass of substance A, the mole-to-mole factors for substance A and B, and the molar mass of substance B. And so the roadmap will look like this. Let's say you're given a mass of A and you want to find out how many grams of B you can produce from that. Because the coefficient in the chemical equations are relating the substances in terms of moles, you cannot change grams to grams directly. You will have to change first the grams of A 2 moles of A using the molar mass of A. And then once you have the moles of A, you will use the mole-to-mole factor that will come from the coefficient in the chemical equation to change the moles of A to moles of B. And then because the question is asking for grams of B, you will use the molar mass of B to retrieve grams of B. And so this type of calculation typically requires 3 conversion factors. 2 from molar masses and 1 mole-to-mole factor that comes from the equation, the coefficient of the chemical equation. So the best way to learn is by practicing and seeing examples first. So let's go through this first example. The fuel heptane C7H16 is designated as the 0 point in the octane rating of gasoline. Heptane is an undesirable compound in gasoline because it burns rapidly and causes engine knocking. How many grams of O2 are required to react with 22.5 grams of C7H16? And so you're given the chemical equation. When you have this kind of problems, you always need a balanced chemical equation. And as an aparté here, I want you to recognize that this is a combustion reaction, right? We have heptane made of just carbon and hydrogen reacting with oxygen from the air to form carbon dioxide and water. Remember that carbon dioxide and water are the only product of a combustion reaction when you're burning a compound made of carbon and hydrogen. And oxygen is always a reactant in this case. So we need to extract the information from the text. And here, it's the last line here. How many grams of O2 are required to react with 22.5 grams of C7H16? And so the given amount here is 22.5 grams of C7H16. So I like to write the given mass under the appropriate compound. So here under C7H16, 22.5 grams. The question is asking how many grams of O2 are required to react with that. So we're interested by oxygen, and we want to find the mass of oxygen that will react with those 22.5 grams of heptane. And so, as I said earlier, the relationship between heptane and oxygen in this chemical equation is given by the coefficient of 1, implied in front of heptane, and of 11 in front of oxygen, sorry. And so the 1 and the 11 here are in units of moles. It's not in units of grams. And so that means we will need to convert the grams of heptane into moles of heptane. And then we can use the mole-to-mole conversion factor to change moles of heptane to moles of oxygen. And then using the moles of oxygen, we can find the grams of oxygen using the molar mass of oxygen. So here is the roadmap, and this summarizes that. So it shows that we will need the 3 conversion factors. The first one will change the grams of heptane to moles using the molar mass of heptane. The second one will change the moles of heptane to moles of oxygen using the coefficient from the chemical equation. And the last one will be using the molar mass of oxygen. So let's write those molar masses and mole-to-mole factors. So to calculate the molar mass of heptane, you take 7 times 12.01 grams for carbon, plus 16 times 1.01 grams for hydrogen, and that gives you 100.2 grams of heptane in 1 mole of heptane. I encourage you to write this as an equality that says 1 mole of heptane equals 100.2 grams of heptane. And as always, out of an equality, we can write two conversion factors. The second equality we will need will change the moles of heptane to moles of oxygen. And this was shown in the chemical equation, the balanced chemical equation that was showing a coefficient of 1 in front of heptane and 11 in front of oxygen. And so we can write that 1 mole of heptane will react with 11 moles of O2. Again, there is two conversion factors out of this equality. And the third conversion factor is the molar mass of oxygen. You take 2 times 16.00 grams for each oxygen atom. And so the molar mass of O2 is 32.00 grams of O2. Again, two conversion factors for this equality. So to set up the problem, you will need to rely on the unit of the given amount. And our given amount was 22.5 grams of heptane. So I will show the full answer now. And so 22.5 grams of heptane is the given amount, and you will start your calculation with that. Remember how it is in the numerator. You multiply by the molar mass of heptane such that the grams are on the bottom and the mole is on top, because you want to cancel grams of heptane. So that's why you place 100.2 grams of heptane on the bottom. You see that the grams cancel, grams of heptane. For the next conversion factor, you want to cancel the moles of heptane. And the next conversion factor is the mole-to-mole conversion factor. And so the 1 mole of heptane will go on the denominator so that it cancels the moles of heptane from the previous conversion factor. And you have 11 moles of oxygen on top. And then you continue by multiplying by the last conversion factor, which is coming from the molar mass of oxygen. For this one, you want to cancel the moles of oxygen in the previous conversion factor. So you will want the molar mass such that the mole is on the bottom and cancels the moles of O2 in the previous conversion factor. And the grams of O2 will be on top. So in the calculator, you do 22.5. So let's do all numerators first. Times 11 times 32.00. And then divide by each denominator. And here only one is valid. Dividing by 1 is not necessary. So we will divide by 100.2. And the calculator answer is 79.0419, etc. And so here we see all the 1 moles are exact, 11 moles of O2 is also exact. All of these are exact numbers. The 2 molar masses have 4 sig figs. And the given amount has 3 sig figs. So the limiting number of sig figs is 3. And so 79.04 will be rounded such that it's 79.0 and not 0.1. So here there is a mistake. It should be 0.0. Okay, so that's our first example showing stoichiometry. Let's go through another example. So how many grams of potassium are required to produce 36.0 grams of KCl according to the following chemical equation? So potassium has for symbol K. And so when we're asking how many grams of potassium, it's the K solid here. Required to produce 36 grams of KCl. So KCl the 36 grams of it are the given amount here. So I like to write that below the corresponding compound. And how many grams of potassium is what we are trying to determine. And we will write a question mark with grams below potassium. So again, the relationship between potassium and KCl is a relationship in moles given by the coefficient of the chemical equation, right? The two you see highlighted here. So that means we will need to convert the grams of KCl into moles of KCl, and then we can change the moles of KCl into moles of potassium. And once we have changed that, we can go back to grams using the molar mass of potassium only. So we need to gather the information, and first the molar mass of KCl. So you take the molar mass of potassium, 39.10 grams per mole, plus Cl is 35.45 grams. Together, that makes a molar mass of 74.55 grams for KCl. Write this as an equality, like this is the best. Next, you want to find the mole-to-mole factor that relates KCl to potassium, K. And so this is given by the coefficient of the chemical equation. And so here it's 2 and 2. So 2 moles of KCl are produced from 2 moles of K. The last conversion factor is the molar mass of potassium. And so this is just 39.10 grams of potassium. So the next step is to write the conversion factors. And you don't have to write all these conversion factors. You could right away find the one that is the one you will use. But from the molar mass of KCl, there are 2 conversion factors, and here they are shown. And we will decide which one we need to use first. And so knowing that we start with 36 grams of KCl, and we want to cancel the grams of KCl, so that means we will need to use the first conversion factor out of these 2. And so after that, we will use the mole-to-mole conversion factor, and it's either of these 2. Given that we will use the first conversion factor to the left for the molar mass of KCl, the next conversion factor should cancel the moles of KCl that are in the numerator of that first conversion factor. So that means the second conversion factor should be, out of these 2 mole-to-mole conversion factors, it should be the second one, the 2 moles of K over 2 moles of KCl, such that we can cancel moles of KCl. The third conversion factor will come from the molar mass of potassium, and given that we are using the 2 moles of K over 2 moles of KCl as the previous conversion factor, we want to cancel moles of K in the last conversion factor. So that means we will use the second one, the one that says 39.10 grams of K over 1 mole. So when we write the full calculation, we always start the calculation with the given amount. And here it's 36.0 grams of KCl. That's in the numerator, multiplied by the first conversion factor, such that grams are on the bottom and we can cancel grams of KCl. And 1 mole of KCl is on top. The second conversion factor cancels the moles of KCl by having 2 moles of KCl in the denominator and 2 moles of K in the numerator. So that changes moles of KCl to moles of K. And then we can go back to grams of K using the molar mass of potassium. And so the molar mass of potassium will be used with the grams on top and the mole of K on the bottom. because this will allow us to cancel moles of K. So in the calculator, you do 36.0. We'll do the multiply the numerators together first. So times, the 1 is not needed, times 2, and times 39.10 divided by 74.55 and divided again by 2 equals, and you should have 18.88128 is the calculator answer. So for sig figs, you know, all the mole quantities are exact numbers. The two molar masses have 4 sig figs, and the given amount has 3. So we will keep 3 sig figs. And so we will keep the 1, the 8.8. And what comes after is an 8. So we need to round up the 8. And so the 8 becomes a 9. And that's why it's 18.9 grams of potassium. So let's go through another example, and you can try this on your own before watching the answer. So in this example, we are dealing with acetylene, C2H2. Acetylene burns in oxygen and produces high temperatures that are used for welding metals. And again, you should recognize here a combustion reaction, right? Acetylene is made of carbon and hydrogens only. It's burning with oxygen from the air and producing carbon dioxide and water. So the question is, how many grams of CO2 are produced when 54.6 grams of C2H2 is burned? So the given amount here is 54.6 grams of acetylene, C2H2. So I write the mass under acetylene. The question is asking how many grams of CO2. And so under CO2, we will write question mark grams. We want to know how many grams of CO2 are produced. So we have grams and we want grams, but the relationship we have between acetylene and carbon dioxide is a relationship in moles. And it's given by those coefficients from the chemical equation. And it says that we have 2 moles of acetylene that will produce 4 moles of CO2. So that means we will need first to convert our grams of CO2 into moles of CO2 to be able to use that mole-to-mole conversion factor and change the moles of CO2, C2H2 to moles of CO2. And then we can go back to grams using the molar mass of CO2 to change the moles of CO2 into grams. So as earlier, we will have to use 3 conversion factors. The first conversion factor will be using the molar mass of C2H2. So this you get from the periodic table. You take 2 times the molar mass of C, 12.01, plus 2 times the molar mass of hydrogen, 1.01, and that's a molar mass of 26.04 grams of C2H2. So that's going to be the first equality you will use. Next, you will use the mole-to-mole conversion factor that comes from the equation coefficients. And we said earlier that 2 moles of C2H2 is producing 4 moles of CO2. And so that's what you will want to use to change moles of acetylene to moles of carbon dioxide. And after that, we can then convert the moles of carbon dioxide to grams using the molar mass of CO2. CO2 is 1 carbon, 12.01 gram, plus 2 times 16.00 grams of oxygen. And that's a molar mass of 44.01 grams for CO2. So here I'm not showing all the conversion factors, but the way to go about it is always start your problem by writing the conversion, the given amount. The given amount and its unit are key for you to know how to start. So it's 54.6 grams of C2H2. The first conversion factor, according to the plan, says that we need to change that into moles of C2H2. So we will use the molar mass of C2H2. So the equality in green here. And because you have grams of C2H2, you want to cancel grams of C2H2. So you will place the 26.04 grams of C2H2 on the bottom of the conversion factor so that you cancel the grams of acetylene. And then the mole of acetylene will go on top. So that first step converts grams of C2H2 to moles of C2H2. The second conversion factor, so you multiply by the second conversion factor, that should change the moles of acetylene to moles of carbon dioxide. And because we have moles of acetylene in the numerator in the first conversion factor, then we want the second conversion factor to have moles of acetylene in the denominator so that we can cancel units. And so you will have then the 2 moles of acetylene on the bottom and 4 moles of CO2 on top. The third conversion factor will convert the moles of CO2 back to grams of CO2. So because the second conversion factor has moles of CO2 in the numerator, the next conversion factor should have moles of CO2 in the denominator so that we can cancel the moles of CO2 as a unit. So moles of CO2 will be on the denominator and the 44.01 grams of CO2 on the numerator. And you see that, you know, all these units cancel until you're left with just grams of CO2. And that's the wanted, that's what we needed to find. So that's this shows how the setup is correctly written. So in the calculator, you do 54.6 times 1 is not necessary, times 4 multiplied by the next numerator, times 44.01 multiplied by the next numerator, and then divide by each denominator. And here there's 2 denominators to divide with. So divide by 26.04 and divide again by 2. And you should get a calculator answer of 184.558, etc. So that's the calculator answer. Again, the number of moles are all exact numbers. The 2 molar masses have 4 sig figs. And so the limiting number of sig figs comes from the given amount, which has 3 sig figs. So 184.558 will be rounded to, so we keep the 1, the 8, and the 4. That's 3 sig figs. But what comes after the 4 is a 5.5. So you need to round up. And so the 4 will become a 5. And you drop everything after that. And so it's 185 grams of CO2. Let's go through yet another example. One that uses ozone and oxygen. So using the balanced equation, how many grams of O3 are formed from 9 moles of O2? And you're given the balanced equation that shows that 3 moles of O2 gaseous using the sunlight will become 2 moles of O3. O3 is ozone, and that's also a gas. So the given amount here is 9 moles of O2, and let's write that under O2. And the question is asking for how many grams of O3. So under O3, question mark, grams. So notice how it's moles that are given, but grams that are wanted. So we will not use the full roadmap that is shown like in the reference information because we already have moles to start with. So the plan here shows that, so hold on. Yeah, the plan here will show that starting from moles of oxygen, you will have to change them to moles of O3. And then the moles of O3 can be changed into grams of O3 using the molar mass of O3. The coefficients here in the chemical equations are highlighted to remind you that those coefficients are giving you a relationship between O2 and O3. But these numbers are in units of moles. It says that 3 moles of O2 will give 2 moles of O3. So let's write the conversion factors. So there is this one that says 3 moles of O2 equals 2 moles of O3. Here it's showing you the 2 conversion factors that are possible from that. And then the second conversion factor will change the moles of O3 to grams of O3 using the molar mass of O3. And you get the molar mass of O3 by multiplying 16 grams times 3 oxygens, and that's 48.0 grams per mole. And there are 2 conversion factors out of that. So now let's put this all together and do the calculation. And so notice here, we need only 2 conversion factors because we started with moles already. So we start with 9 moles of oxygen, 9.0 moles of oxygen. We'll multiply by the first conversion factor that will change those moles of oxygen to moles of ozone. And we will choose the conversion factor that has moles of O2 in the denominator because our given amount has moles of O2 in the numerator. And so this will allow us to cancel moles of O2. For the next conversion factor, we want to cancel the moles of O3 that are in the numerator of the first conversion factor. So the second conversion factor should have mole of O3 in the bottom so that the moles of O3 will cancel. And so the molar mass in grams will go on top of the conversion factor. And you see that when all units are cancelled, you're left with grams of ozone. And that's what we want. We wanted to find the grams of ozone produced. And in the calculator, you do 9.0 times, so let's multiply all numerator together first. So times 2 times 48.00, and then divide by each denominator. And here there's only one that is worth typing. So divide by 3 equals. So the calculator answer is 288 grams of O3. However, if you look at the number of sig figs, what is limiting is the given amount again. It has 2 sig figs, 9.0. The 0.0 here is significant because we see the dot. So 2 sig figs, the 48 grams of O3 here are not limiting. So, and again, the 2 moles, 3 moles, or 1 moles are exact numbers. So keeping 2 sig figs when you have 288, so you keep the 2 and the first 8. What comes after that 8 is another 8. So you need to round up, and that's why the 8 becomes a 9. It becomes a 9, but you have to show that you are in the 200s. And so you need to add a 0 to show that the 2 is in the hundreds place and the 9 is in the tens place. And so it's 290 grams of O3. And you pay attention to not show the decimal point because otherwise it would make 3 sig figs. Okay, so here we have 2 sig figs.